We're ready for part B of exercise 6. So this is a totally separate problem. Similar to what we did, but there's a little added twist to this one. So we have to construct a polynomial using the given information. Let's go ahead and do that. And so it says we want to have zeros 2 and I, and we want f of 0 to be equal to -6. Now they don't say anything about multiplicity of zeros here, so we just assume we have multiplicity 1, right? They want 2 to be a 0, I to be a 0. We don't have to put in more factors than we want, so we will just assume multiplicity 1 for both of these. What we got to notice here, though, is because we have this non-real complex 0i, we know that minus I, the complex conjugate, must also be a 0. So there's actually a 0 they're not even telling us, and to make this problem work, we have to include this other one. This is really based on the complex conjugate theorem. So because I is a 0, its conjugate minus I has to come along too. So we actually have to have 1, 2, 3 separate zeros for this to work. Now let's start putting our function together. If 2 is a 0, then x minus 2 is a factor. If I is a 0, x minus I is a factor. And if minus I is a 0, x minus a minus I, or x plus I, is a factor. And so we'd like to just stop here if we can, but we have that added condition that f of 0 is -6, so let's plug in 0, see what we get here. Here in this factor I get 0 minus 2 is minus 2 times 0 minus I is minus I, 0 plus I is I. So I get minus times minus is plus 2. I get 2I squared, which is 2 times -1 or -2. I don't get minus 6. So I have to introduce a scaling factor and find a value for the scaling factor. So we got to find a value for A. And what I'm going to do is I'm going to take what I have and plug in 0. So f of 0, I won't try to do this in my head, f of 0 is A times 0 minus 2 times 0 minus I times 0 plus I. And we want that f of 0 to come out to be -6. So that's A times -2 times -I times plus I. So -6 would be negative times negative is positive. It looks like I get 2ai squared, right? So -6 equals 2a. Now I got to replace that I squared with -1, right? I squared is -1. So this actually says -6 is equal to -2a. And so when I divide by -2, I get a, or 3 is a. A is positive 3. So here's my function f of x is 3 times x minus 2 times x minus I times x plus I. And there's a factored form for our answer. Factored form. Now there will be problems where I say you have to multiply it out. So you want to make sure you can do that. There may be some where you can leave it in factored form, but we're going to go ahead and multiply this out. And so to do it, I'm going to start on the end again, kind of like the previous problem. I'll multiply x minus I times x plus I. I get x squared plus ix minus ix minus I squared. All right, so what do I got here? F of x is 3 times x minus 2 times x squared. Ix minus Ix is gone. And now I'm going to write it out in a few steps because I want to make sure everybody sees what's going on here. It looks like x squared minus I squared, right? But I can simplify that I squared. I squared is negative 1. So make sure you realize there's a minus sign already in that expression, but the I squared introduces another minus sign, so we have minus a minus 1. And so this is actually x minus 2 times x squared plus 1. So the i's have disappeared, and there's just x squared plus 1 resulting from those two factors that had the I and the minus I. And that's kind of what the conjugate does. What the conjugate does is it makes the i's go away when we multiply out, and then we get a polynomial with just real number coefficients. Now I got to keep multiplying here, so I'm going to now do x minus 2 times x squared plus 1. I get x cubed plus x minus 2x squared minus 2. And if I distribute my 3, I get 3x cubed plus 3x minus 6x squared minus 6. There's the multiplied out. So here it's really nice to see how simple the multiplied out form is, in a way, with none of that I business, none of that imaginary. It's buried in there, but we don't see it. Okay, so we're done. And again, just be aware, I may ask you to multiply it out. I may ask you to leave it in factored form. But now let's just do a little bit extra. And I want to sketch a graph here. Now, we have only one real zero at 2. And we have a y-intercept at negative 6, right? I'm just going to use a different scale here on the y-axis. So we have a y-intercept point there. This is a 0 of multiplicity 1, so the graph just crosses across. Our end behavior is like x cubed, so we know the graph goes up here, down here, basically. Now, what goes on in between, it's not so obvious if there's a wiggle or no wiggle. It's almost like you want to just connect those up. And if you did, from what we know, that's acceptable. But actually, I checked on Desmos. This graph has a little bit of a wiggle and then takes off. So the real graph actually dips down, comes up again. So it has that cubic kind of polynomial wiggle to it. And we don't really, I used Desmos to show me this. Without using Desmos, I just have to plot a lot more points, okay? But even beyond the wiggle, what I want to think about here is we have this third degree polynomial. On the graph, we have just one x-intercept. So even though it's degree 3, there's only one real 0. One real number 0 is 2. And there are 2 complex, I would say non-real zeros. The I and the minus I, they don't appear anywhere on this graph. So it's interesting that the graph only has the real number information from the polynomial. Okay, so they're factored out form and the multiplied out form. And as a bonus, not required as part of the problem, we drew a graph. So we got one more, and it's actually going to be the trickiest one of all now. So the grand finale of this topic is coming up next.